Minutes left in the video and it just just stopped.
No, you said something like you're gonna turn it off to do something and then turn it back on and
Oh, no.
you forgot to record it or didn't.
Okay. All right. Then they changed the buttons on the record. Let me see. It used to be down at the bottom. This is kind of a black sludge, is the way I describe it. Hot black sludge. And so you'll have a violent reaction initially. And the violent reaction, you'll talk about it tomorrow in lab. And so with this hot black sludge, then we're going to let it cool down a little bit. And then add the ethanol. Did I talk about the ethanol? No. All right. And so how much ethanol do we add? Well, we add lots of ethanol, actually. Look.
Yeah.
10 milliliters of ethanol? Okay. 10 milliliters is just kind of the guideline. Oftentimes what we do is we modify the procedure depending on what we observe. And so with the 10 milliliters of ethanol, what does it say you're going to observe? Especially after the cooling stuff. And so we let this cool a little bit, and then we just add some ethanol. 10 plus milliliters. Let's just do to this. And what should you observe? Crystal formation. Now, if you don't see a lot of crystal formation, then just keep adding more ethanol. So if you add 10 milliliters of ethanol and you're barely seeing anything happen, then the best thing is to add more. So this is why I say plus, because here we should see crystals. What color are the crystals that we should see form? So this is what you're going to be looking for. Like a green, black, green violet crystals. You should see form. And so we want to see crystal formation. And then we're going to cool it in an ice bath. Usually when you cool it in an ice bath, things become less soluble. As you heat it, it becomes more soluble. And so we're going to cool it to try to maximize the amount of crystals that we form. And so ice bath this. When we ice bath this, we get ice. Ice alone doesn't have good thermal conductivity, so we use ice water. Ice water is the best in terms of cooling things down rapidly. If you just use ice, then it takes a long time to cool down. So ice water will cool it down faster. What we want to do is we want to maximize crystals formation. And that's the end of day one. And so this would be the lab notebook prep for day one. I usually just draw little pictures like this. I don't like to read a lot when I'm doing lab. But if you like to write down, verbal instructions, that's fine. The lab notebook is primarily for you, and then it's also for others if they need to repeat, the experiment. So based on what you've written, this is how you know you're writing enough. You're writing enough so that if your friend tried to repeat the experiment just like you did it, they would be able to do it just like you did it with the same masses, the same volumes, everything. Like I said, we don't always do 10 milliliters here. So if we have like 15, 20 milliliters, we'll write that down on the observations side. The observations is just to correct the procedure for what we actually did in lab. Procedure is written procedures written in the present tense, but observation is always written in the past tense, future or present tense for procedure. And so when you read the observations, you should be able to tell that you actually did this. So for example, this is not a good statement for observations. Add 20 milliliters of water. Well, add 20 milliliters of water. Did you actually add 20 milliliters of water? And so for observations, you have to say something like 20 milliliters of water were added to whatever. That would be, or you just say 20 milliliters H2O, check. If you have it next to the procedure. This is just things to speed up. This is not a crazy busy lab. There are some crazy busy labs where you barely have time to finish, or you might not even finish. And if you don't finish, then they don't really care. When I was a student, if you're not able to finish, then they think that you were unprepared. And so if you come in and you are struggling to finish, then they think, okay, you didn't prepare well enough. Because if you prepared well enough, you should have been able to finish the lab. That's the whole thing. And then when I was at UCLA, for every for every 1 second we went over time, it was like a 1 point penalty. So if we went 10 seconds over, it was 10 points. Because, at UCLA, it was like, I think we had 5 minutes or 10 minutes before the next lab comes in. The labs are constantly run. So if people are going overtime, then it slows down the next lab. And so they kick you out and they penalize you if you aren't out in time. So this is why when I was a student at UCLA, I spent a lot of time preparing before lab to make sure that I could finish, because some of the labs were hard to finish, pretty hard to finish. Well, anyway, this is going to be worth some points. So just prepare your lab. It's not that difficult. I mean, there weren't too many steps here. We're going to have a lab, qualitative analysis, with a lot of steps. People get lost. During the qualitative analysis lab, people always come up to me and ask me, because they're totally lost. It's like a maze. And, they don't know where they're at. So this kind of gives you a mental picture of what's going on in the lab, so that you can be better prepared. Yes. Okay. No. Physical, I'd like it. Physical during the test. So for example, when we have our chapter 15 exam, just bring your chapter 15 homework that day, and then I'll just check it off, that kind of thing. I think what I'm going to do is I'm postponing this chemical reactions and nomenclature, because we're going to get more practice with chemical reactions and nomenclature, and so we'll kind of you'll be kind of tested on that later in the semester. They've had more time to get more comfortable, hopefully, with the material. All right, any other questions? Uh-huh.
Is there a test date?
No, there's no test. It depends on our schedule. I'm usually, the syllabus is what I ideally like to do, but sometimes I get behind, or usually I get behind, so that's fine. So the test date will be a week after we finish. So when we finish chapter 15, which will probably be today, the next week we'll have a test on chapter 15. That's kind of how it works. Test will be like 1 page long, or maybe 2 pages. Most likely just 1 page. It's not going to be a very long test. Okay, so let's take a look at chapter 15. And so were there any other questions on the lab? I'm going to talk more about the lab in the morning. There's going to be some modifications to the procedure. So I'm going to add a step. All right, so to determine K requires some work. Measuring the equilibrium concentrations isn't so easy. Fortunately, there are other people who did a lot of the work, and so we can benefit from them pretty much. Other people did a lot of the work and compiled it into tables, but sometimes there's K's that aren't known. And so do we always have to do an experiment to determine K? And the answer is no, we don't always have to do an experiment. There are some relationships that we can use that'll help us determine the K is called the equilibrium constant. And what are those? So we talked about KP and KC. I think that's where we left off. Is that right? What number did I call KP, KC? Did I give it a number? I just said KP, KC. Okay. So we talked about the relationship between KP and KC. So we can. So for example, if we measure the concentrations and determine the K, we don't have to measure the pressures. You know, we can get the pressures from concentration or vice versa. All right, then there are going to be a series of Hess's law style. These aren't, you know, technically Hess's law, but just say Hess's law style application. And so let's say we reverse the equation. So we're looking at GG plus HH plus ... goes to AA plus BB plus ... And so we reverse the equation. Now what was once the reactants is now the products. And what was once the products is now the reactants. So what do you think the K is going to look like for this? Yeah, it's going to be inverted. So K for the reverse reaction is just 1 over K for the forward reaction. And so we just flip it over because we just flipped over the reactants and the products. And so this is often pretty useful because sometimes when we're looking at the reverse reaction of something that's already known, so we don't have to figure it out. Okay, the next Hess's law style thing is sometimes you multiply it by some coefficient. And so we'll multiply it by some coefficient, we'll just call it, what should we call it? We'll just use all those letters. And we'll call it X. So now if we take our normal AA plus BB goes to GG plus HH. So let's say we double it or cut it in half or cut it by a quarter. What should we do to K? Yeah. So K is just going to equal K of the original raised to the X power. Okay, then the next thing we look at is when we add. You know, Hess's law, we add equation 1 plus equation 2 gives us a net equation. You guys remember doing that with the delta H's?
Let's say GH.
GG. Oh, HH.
The first thing.
GG.
Yeah, the very first thing.
Yeah, GG, HH.
Yes. No.
So when we add up equations like equation 1, equation 2, So equation 1 plus equation 2 plus however many equations there are. And then we know, this is K1, this is K2. When we do Hess's law, we add the delta H's or the delta U's. But here, what we're going to do is K for the overall or the net equation. So this is going to equal the net equation. K for the net equation is going to equal the product of the K's. So you multiply the K's rather than add the K's here. You can, if we just mapped it out, canceled everything out, then we'd see that, we could prove this pretty easily. Well, I'm not going to prove it. I'm just going to use it. Okay, so those are other ways of determining K. There are more. This is going to be in another chapter, I think. The more comes from thermodynamic calculations. Uh-huh.
So, where's the equation 1 plus equation 2, and then you label equation 1 as K1 and the second one is K2, and that adding those equal the equation net, and then K net is multiplying them instead?
Yeah, for the K, equilibrium constants. So this is a very powerful method here. This is going to be the most powerful method that we're going to use to calculate K values. We can calculate K values using thermodynamic data. And this allows us to determine the K's by calculation for many, many reactions without actually having to do any experimental work. So that's a big advantage. But we aren't going to talk about that until we get to thermodynamics part 2. Try this again. See if this is going to look. Having trouble loading the textbook here. Okay. Textbook isn't working. Let me look at some K table. I'll make up some problems here. Okay, one of the chemical properties are Lewis acid-base reactions. So we want to know, okay, what types of things can you expect for Lewis acid-base reactions? So we have a table similar to this in our book. And so when we're thinking about what kinds of complexes form, these are hard to predict. Can you predict these? Or would you have predicted these? So for example, copper, would you have predicted 4 ammonias, 2 ammonias, or 6 ammonias? No, you couldn't have predicted that. And so this is just based on observations. This is based on observations. What we're going to do is we're just going to look at these once in a while. Actually, the more you look at these, the more comfortable you're going to be with these complexes. So the first step is the observations. And when we have observations, sometimes the observations are this, there's a whole bunch of seemingly random observations, but they aren't totally random observations. There's some patterns to this. And so how do you recognize some of those patterns? Recognize some of those patterns by just looking at the observations, over and over again. That's all we do. This is how the scientific method works. Can you give me a hypothesis? Hypothesize, you're going to predict what complex is going to form. Come up with a hypothesis. You're not going to come up with any hypothesis. Who's going to come up with a hypothesis for that? It's too hard, right? And so this is why, what I'm telling you, most of the people I work with and myself included, we're just doing this. We just got a whole bunch of observations and looking at the observations, over and over again. Then maybe we can come up with a hypothesis, But let's read these off. Can you name these? Let's just quickly name these. Diamine, silver 1 ion. Diamine silver 1 ion, we saw that in lab last week. We didn't see this one though. What's this one called? Dicyano or cyanido, with either one's fine because both are, actually cyano is probably more common, but cyanido is what the book says now. Dicyanido or cyano, argentate, argentate 1. The 1 comes from this negative charge, true or false? The 1 comes from the negative charge, the Roman numeral? No. Where does the 1 come from? Yeah, charge of the silver. Cyanide's minus, so we have -2 plus 1 gives us -1. Plus 1 comes from this one. Okay. Okay, dithiossulfato. So thiosulfatos, what's the charge on thiosulfate? -2. So this -2 times 2 is -4. -4 plus what gives us -3? Plus 1. So this is going to be dithiossulfato or sulfato, argentate, Roman numeral 1, ion, right? Is thiosulfate, is that a monodentate, thiosulfato, thiosulfate, whatever? Is that monodentate or bidentate, or what is that? We looked at thiosulfate, though, back. How's your recall?
I have a question. Would it be this?
No, it would not be bis. The reason it wouldn't be bis is thiosulfate does not have the first. We start off with the first numbering system. If thiosulfate already had the first numbering system built into the name, like for example, ditri tetra, then we'd have to use bis. But thiosulfato does not have the first numbering system, so the first instance of numbering is going to be the first numbering system, which would be di. Monodentate, yeah. And so already, what pattern do you see? Silver likes to form what we call linear complexes with a coordination number of 2. Okay. Let's go on to this one. Name this one for me. Okay. Yeah, tetrabromo, correct? Cadmium or cadmiumate? Cadmiumate. Although that sounds awkward, you know, we don't have any choice because there's no fancy name for cadmium that we can use. And so tetrabromo cadmiumate, 2. Plus 2 is the charge here. Bromide's minus 1 times 4 is minus 4. Minus 4 plus 2, that gives us minus 2. So cadmium plus 2. So bromium 2. Let's go to this one here. Yeah, hydroxide or hydroxide. So tetrahydroxido or cido doesn't matter. Chromium or chromate? Chromate, and the charge on chromium? Yeah, it's going to be plus 3 because this is minus 1 times 4 is minus 4 plus 3 gives us minus 1. So it's Roman numeral 3. And if we look at cadmium, we don't know if that is a tetrahedral complex or a square planar complex. We just know its coordination number is 4. Well, it turns out for cadmium, this is a tetrahedral complex. Cadmium. And the reason is one of the hypotheses is because you look at the d electron configuration. You know, when we look at the electron configuration with cadmium 2+, cadmium 2+ is argon 3d10. And so it's got a filled subshell, the 3D subshells filled. And so we'll see that when the orbitals are filled, that is, they have that symmetry, then they tend to form tetrahedral complexes. The ones that have partially filled Ds tend to form square planar. Well, let's take a look at this chromium. This would be, oh, we already did that one. Let's take a look at this cobalt. This ligand is a bit tricky. Yeah. It's thiocyanate. Cyanate is OCN. Thiocyanate is SCN. And this is 1 minus. And so this is tetrathiocyanato. Cobalt or cobaltate? Cobaltate. Charge on cobalt? 2. Yeah, that's 2. We would, we just look at the observations. The structure of this isn't even given here on this table, so we'll just skip the structure. I don't know, whether it's tetrahedral or square planar, we need to see more examples, and then maybe we can see a pattern with that. Let's go to this one. Charge on copper. 2, yeah. This one we saw. This is the deep blue ion. What about this one here? Yeah, good. These are 4 coordinate. This one? Yeah, equal to 1. Hexamine equal to. This one? Yeah, hexacyanoferrate, cyano, either ferrate. What was the charge? 2. How about this one? Yeah, good. All right, now this is the Lewis acid here, the metal. This is the Lewis base, we call the ligand. Now, are these reactions favorable? Well, let's take a look. Which one's favorite, the product or the reactants here? Okay, we're going to look at K. KF, F stands for formation of metal complexes. This is the formation reaction here. This is Lewis acid base reaction. Now, when we look at these ratios, does it heavily favor, well, looking at it overall, does it heavily favor the reactants, products, or is it kind of a mix of both reactants and products? Yeah, this is heavily favoring the products. I mean, this is the smallest one here, and that's already 1,000, But we have the huge one here, 42, 10 to the 42. How big is that? That's just enormous as far as that goes. Okay, so we have these reactions. So let's take a look at, let's do this one first here. Now this is 10 to the 7th here. I'll try that one. And so what we're going to do here is the K has already been determined for us. So we don't have to do anything. We're going to apply K. And so I was going to do some problems with determining Ks using this Hess's law, if I can get the book to load. But Hess's law, did you find Hess's law problems difficult or pretty straightforward? Maybe I should use the PowerPoint. I don't know. Okay. So we're going to apply, this is determining K. And so the next step is, okay, if we have the K value, which we do from this table, then we can do stoichiometry with K. And so the first one we're going to do is this reaction here. And so what we'll do is let's put a beaker here. And what we're going to do is we're going to make a solution. This solution is going to be 0.100 molar silver ions, Ag+. And so we need something like silver nitrate, silver acetate, some soluble silver salt to give us that. It doesn't matter what the salt is. And then to this, we're going to add ammonia. We're going to add ammonia to make this solution 3 molar in ammonia. And so it's going to come out 3 molar ammonia. And then we know that ammonia and silver, really that's 10 million or 17 million. 17 million to 1. Ammonia and silver really like each other. Is the K is telling us this is heavily product favored. And so the reaction that's going to happen here is this. Here's our Lewis acid, and then it's going to be attacked by 2 ammonias. How do I know? I just looked up on the table. And it's going to form the diamine here. Okay, it's not 100%, forward reaction. So what we're going to do is we're going to calculate, what we expect at equilibrium. So then this is what we call the initial silver, 0.100 molar here. And the initial ammonia is going to be 3 molar here. Actually, let me go with this. 3 decimal places. We'll make it more precise. That way I don't have to worry about too much rounding. And then what we say is that, I just mix it together, nothing's reacted yet. And then we let it react and reach equilibrium. So there's going to be a change, but, I wouldn't say the change is complete because K is not infinite. K is finite. K is going to be 1.7 times 10 to the 7th. I mean, it's huge. So we expect to lose a lot of it. Okay, so let's go ahead and do this. So we're going to call it minus X molar here. And then this is going to minus, now we're going to do stoichiometry for this. So for every X I lose for silver, how many do I lose for ammonia? 2. And so what I'm going to do is I'm going to call this minus 2X molar here. And then this is a 1 to 2 to 1 ratio, so this is going to be plus X molar. So I'm going to lose probably a lot of my silver. It looks like, because the limiting reagent, can you tell what the limiting reagent here is? If I use up all my silver, how much ammonium will I have used up? Well, if I use up all my silver, let's say 0.1, then I need 0.2, but I have 3 molar, which is way more. So this is in large excess. This is limiting here. But we don't know where it's going to end up. It's going to end up here, 0.100 minus X molar. Over here, it's going to be 3.000 minus 2X molar here, and this is going to be X molar here. Okay, now we're going to solve for X by just plugging it into the K expression here. The K expression is going to be the concentration of the diamine silver ion divided by the concentration of the free, we call this as free silver. This is called the complex silver. The free silver. This is called the complex silver. So I want to figure out, how much free silver I have, how much complex silver I have once this reaction is finished. All right, and then this is going to be times the ammonia concentration. But what do I have to do to the ammonia concentration here? Yeah, I need to square this here. Okay, then what we're going to do is we're going to plug in this. So the diamine silver is X. The silver is 0.100 minus X. And then the ammonia is 3.000 minus 2X quantity squared. You guys like algebra?
That's your question?
Well, some people like algebra. They think that some people think algebra is easy, or some people think it's pretty hard. Algebra can be pretty hard. This one's looking easy to you or hard? All right. Okay, why don't you solve this one for me? Solve for X. One thing you could try is to get it in cubic form. Ax cubed plus bx squared plus cx plus b. And then plug it into calculator. Like if you have one of the calculators that can solve the quadratic, it can solve it to cubic equations. However, getting it into cubic form is probably not so easy. I mean, maybe not so difficult, just time consuming. Just plug it in. So when the math gets difficult, third order polynomial, seventh order polynomial, how are we going to solve that? We have the setup here. We just need to figure out how to solve it. And so we have to have mathematical tricks, mathematical tricks to be able to solve this. And so what are the mathematical tricks that we can use to solve this? One thing is this. When you look at the forward reaction, which one's going to be favored? The forward reaction or the reverse reaction when you see something like this? Forward. And do you think it's going to be heavily favored or? it's going to be heavily favored in the forward direction. And so let me show you, I'm going to show you a number of mathematical tricks, and it probably confuses a lot of people, because a lot of people, when they do math, they don't like to do these, because math is supposed to give you the right answer, and they don't want to make assumptions. But if you want to do this properly, then go ahead and solve it. That would be better, if you could do it. But most people can't solve that. And so we're forced to do these things. And what are they? Well, one of the things we do is this. One of the things we do is we try to make the change small. We try to make the change small, because if we can make the change small, then we can make an assumption to make the polynomial smaller. So for example, 0.100 minus x, is the change going to be big, or is the change going to be small? Well, 0.100 minus x, I'm talking about the minus x here. Is the x going to be big or small? The change here. Yeah, 0.100 minus x, the change is going to be big going in the forward direction. 3 minus 2x. Well, 2x is, well, not so big compared to this, right? Because this is in large excess. But when we look over here, this change is big compared to this. Even if we had complete reaction, this would be 0.2. Well, 0.2, we're going to lose a little bit then. And then over here, the change is going to be big, because we're going from 0 to x. And the x we already know is kind of big. And so one of the things we want to do is we want to do this. Let's say if all the atoms are over here on the reactant side, and they want to be over here on the product side, this change is going to be big. So what we want to do is we want to take all the atoms on the reactant side and then move them over to the product side. If we do that, then we'll let some of the product go back to reactant. And the amount of product that can go back up to reactant is going to be very small, because it's kind of steep hill to climb, right? And so right now, everybody's going to fall off the cliff. Everybody. So what we're going to do is we're going to just force everybody off the cliff, and then down here, and then see how many can make it back up. Why are we going to do that? It'll become clearer in a minute, but here the change is big. So our first trick is we're going to try resetting all the atoms. In other words, we're going to push all the atoms off the reactant side and push them down to the product side. And so this is called a reset. The only reason you'd reset is if it's misbalanced like this. Everybody wants to be on the right side, but everybody's on the left side. If everybody wanted to be on the left side, then you leave it alone. This is good, because change should be smaller. All right, so one trick is to reset the initial conditions. And equilibrium, it doesn't matter, as long as you have the total number of atoms, you didn't lose any atoms, you're going to reach the same equilibrium as you would without that. And so as long as the number of atoms does not change, we're okay. Okay, so my original initial conditions will be here, 0.100 molar and 3.000 molar and 0 molar. And so I'm going to reset all the atoms to the product side. So here, reset to right. When I reset it to the right, I have to pay attention to what my limiting reactant is. And so in this case, I'm going to call it minus y minus 2y plus y. And so here, y is going to be complete. I can't throw all the atoms to the right, but I can, because of the limiting reagent issues. And so what's the limiting reagent here? The silver or the ammonia? The silver, so Y is going to be minus 0.100 molar. That's what Y is going to equal. Okay, that means 2Y will be minus 0.200 molar. And plus Y will be plus 0.100 molar. And so this will be my new initial conditions. My new initial conditions will have 0 molar silver ion, 2.800 molar ammonia, and 0.100 molar of the complex. And so this is, this is as many atoms as I could throw on the product side. Okay, then what I'm going to let it do is I'm going to try to figure out how many can make it back up the hill, which is going to be very few. And so here, then it goes back to what we have here, except now I'm looking at how many they get back uphill, which will be plus X over here, plus 2X over here, and minus X over here. So then at the end of this, we should have X molar, 2.800 plus 2X molar, and 0.100 minus X molar. Yeah. Okay, now we're going to plug this into K, which should be just the products of the reactant. So this is going to be 0.100 minus X on the top. Then we're going to have X over here, and then 2.800 plus 2X squared. Yeah. Well, number one, does the algebra look a little easier? This one, I think we could get into cubic form. Let's go ahead and do that. Sometimes the algebra comes out easier, sometimes not. I don't know how to do it.
It doesn't look any easier. It doesn't look any easier. It looks almost exactly the same. Just
Then. I got my hopes up, but it didn't quite work out. All right. If the change is expected to be small, so when we look at this, this heavily favors the product. So going backwards, we expect very little, right, change to occur. If change is small, so small it's negligible. Now, negligible only means initially negligible. Later on we're going to factor in the change. I'm going to put negligible in quotation marks here because it's not really negligible in the sense that we ignore it at all times. But for our purposes of our calculation, we're going to ignore this right now. And so what that means is this. Then 0.100 minus X, how many of these are going to make it back up that steep hill? Negligible. And so 0.100 minus X is going to be about 0.100. Very, very tiny population will make it back up the hill. And then we can do this. 2.800 plus 2X, we're going to get a tiny amount going back. And so that tiny amount is compared to 2.8 is going to be nothing. And so here, this is going to be about 2.800. We're not really going to add much ammonia back there, even though it's a 2X. How about this one, X? Well, X is significant because this is going to be 0 plus X. 0 plus X is not going to be 0, And so the other one was 0 plus X which gave us x, which is not equal to 0. All right, now what we're going to do is we're going to do this. This is called the simplifying assumption. And the simplifying assumption is a very common technique to help you with the math. Because the math becomes too overbearing. And so if we apply the simplifying assumption, then, it's not perfect, right? Because we are making an assumption that we ignore it. So it's not perfect algebra. And so on the top, it's going to be 0.100. And then on the bottom, it's going to be x times 2.800 squared. Now, how does the algebra look? Yeah, much, much better. And so what we want to do is we want to solve this for x. So can you solve this for x? Yeah, this will be much easier to solve for x. I think I can even do it here. So I got x is equal to 7.503 times 10 to the 10 to the minus 10. Is that what you get? Okay. So let's give it a try here. Now, it's negligible just to solve. And so when I say negligible for solving for x, not negligible for solving for equilibrium concentrations. So this is what we're going to do. How many sig figs are we allowed? Like 2 sig figs. But I'm going to carry extra. I'll tell you the reason why in a bit. Okay, so when we solve for the equilibrium concentrations, we go back here and then plug them in. And so my x is equal to 7.503 times 10 to the minus 10. And so the silver ion, the free silver ion concentration, 7.503. I'm going to subscript these here because they aren't significant, times 10 to the minus 10 molar. 10 to the minus 10 molar is nanomolar. And so this is like a 10.75 nanomolar. It's barely anything in there. Okay, let's calculate this one. So how much am I going to add to this? So that's going to be 2.800 plus, okay, now I'm going to write this in decimal form. 7.503 times 10 minus 10 gives me 9 zeros after the decimal. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 7, 5, 0, 3. So when I add this, I'm going to get 2.800 000007503. I'm allowed 3 decimal places here. Was that pretty negligible? Yeah, that's pretty negligible. So let's check this one here. So this is going to equal 0.100 minus 9 zeros after the decimal. 1, 2, 3, 4, 5, 6, 7, 8, 9, 7, 5, 3. And so this is going to come out to 0.099. Actually, do this in your calculator. Tell me what you get. You can put it in scientific notation form, 0.1 minus 7.5 times 10 minus 10. Okay, how many nines? 8 nines. You have a good calculator. For 8 nines and then what? 2, 5. Or 2, 4. Okay, those are good calculators. We'll drop the 03. Just go with 7.5. That's all. Is that what everybody got? Did anybody get 0.1? No? All right, that's good. All right, so this is our stoichiometry. Our stoichiometry is, I mean, this is practically complete reaction here. Can you tell me what the percent reaction is for this? All right, so the percent reaction is going to be the amount of reaction from the initial. This is the real initial. And so we have to use the real initial, not our reset initial. And so the real initial amount is 0.100 molar. How much reaction did we have going from 0.100 to here? So we have to subtract these two. And so that's going to be 0.100 minus 7.503 times 10 minus 10.
And just the initial amount of the limiting reagent?
Yes.
The amount of reaction or at reaction?
The initial amount of limiting reagent, if we use the initial, this, we could get the percent reaction of ammonia. But the percent reaction of ammonia is tricky because we could have reacted more ammonia if we had more silver. And so this is why we base it on the limiting reagent. So that's a good point. Use LR, limiting reagent, for this. Well, we already did this 0.100 minus 7.5. Here it is. It's 0.0999989. 0.0. Then we'll just put in 8 nines here. Or 8 nines and then a 2 5 over 0.100 times 100%. So we got that here, times 100%. So we have 99.999925% reaction. That's pretty close to 100% reaction. When you say, I mean, if we rounded this to proper number, 6 days, we had 100% reaction, but then we didn't have 100% reaction, right? Because a tiny amount didn't make it back up the hill, and this is what we're interested in Chem 1B. In Chem 1A, we probably would have ignored it and just said 100% reaction. But in Chem 1B, we're going to do these kind of what we call equilibrium stoichiometry calculations. Now, is there a way to double check this? I mean, this looks good. Is there a way I can double check mine? Well, you could say, oh, look it up in the book, check your answer in the book. What if the answer's not in the book? How could you see if you got the correct answer? Or if this were on a test, if it were on a test, then the correct answer is not there. And so the way we double check our calculations is like this. The way we double check our calculation is by doing a calculation for K using these concentrations. If I plug these concentrations in for my K, then I should come out to 1.7 times 10 to the 7. So let's try it. So I'm going to go ahead and plug it in. So in the numerator, I'm going to get 0.0 and then 8 nines. The reason I carry extra digits is because of this. If I round this, I'm going to be subject to round off error. If I'm subject to round off error, then I'm going to be off. So let's say the K is a little bit different. Let's say the K came out to 1.6 times 10 to the 7. Is that because I made a calculation error, or is that because I did round off error? And so to eliminate the possibility of round off error, I'm going to carry a lot of extra digits so that there's no chance of round off error. Usually, how many digits is that? You usually carry 1 or 2 extra digits, but I'm going to go a bit more. So for example, if we were to round this, what would you round this to?
1.
Yeah, 0.1, 2.8, 7.5. And it's going to come off a little bit, but if I don't round it, let's see what I get. I'm going to 8 nines, or 8 nines, 25 numerator, divided by the silver ion concentration. So I'm going to carry all digits here. 7503 times 10 to the minus 10, divided by the ammonia concentration squared. So this is going to be 2.8. And then I'm going to have how many zeros here? 3, 6, 7, 8 zeros. Or 9 decimal places. So 3, 6, 9, and then 7503. In fact, I can make this even more precise. For example, here, rather than doing this, I would have done this 2497. Then there should be no round off error. I did that because that 25 was rounded. 2497. All right, so now let's plug this into the calculator. Plug this into the calculator, get 0.0 and then 8 nines. 0.0, 9, 1, 2, 3, 4, 5, 6, 7, 8 nines. 2497. One, two, three, four. 1, 2, 3, 4. 2, 4, 9, 7. My calculator maxed out in portrait mode. I couldn't enter all the digits. Divided by 7.503 times 10 to the negative 10 equals divided by 2.8. And then 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. 7503. What did you guys get? You got 1.7?
0, 1, 2, 5 zeros.
Okay, so you got a K 1.7 with 5 zeros.
And then 2, 7.
2, 7 times 10 to the 7. Okay, so that's a pretty good match, right? And so this tells us we did the calculation correctly. we got the right equilibrium concentrations to give us a K. Now, when you do, like I said, when you do a lot of rounding, this can come up way off, like 10% off or 20% off, and then you don't know, did I screw up the calculation? Or is that just because I rounded? And so normally when I do these equilibrium calculations, I carry extra digits, so I can always check it to make sure, and then have confidence that it came out okay. How much time do we have? 5 minutes? Okay. Do you think you could do this one in 5 minutes?
I don't know if I did it wrong, but I got a different number as well.
Oh, did you swear this one? Yeah. I didn't write that. I didn't finish writing that. That's fine. Or just take your number and divide it by 2.8 again, and then see if it comes out right. Hopefully it does. Let's see if your calculator can handle this one. Because your calculator has a limited number of digits, and your calculator rounds off. And if your calculator rounds off, that could screw up your calculation as well, because your calculator can't carry an infinite number of digits. And so we're going to do this one on the bottom. And so the one on the bottom is going to be this. It's going to be, we're going to take Fe3 plus. Come on. Fe3 plus 6 cyanide goes to FeCN6. Now we got brackets on brackets, which is a bit of a pain, but it's all right. Just get used to it. And then K for this is 1 times 10 to the 42, which is an enormous number. That's huge. Okay, so what we're going to do is we're going to be given these initial conditions. We're going to start off with 0.1 molar iron 3 plus. And the cyanide, we're going to go with, let's go again with 3 molar. Which one's the limiting? Which one's the excess?
Iron.
Iron's the limiting, right? And so we have plenty of cyanide to do this. The more cyanide we put in here, the more pushes it to the right, the Chalet's principle. The less cyanide, the more leftward it goes. All right, so try this one, or at least get it set up and see. Or actually, we'll leave this one for homework too, if we run out of time.